Today we will continue. To consider kinematics, and then we will start. To talk about dynamics. As I can remember, we spoke about angular velocity and angular acceleration. Angular velocity and angular acceleration. We have had a look. At rotation of perfectly rigid body. I'll remind this. We can set some reference system x, y, z, where z is the axis of rotation. The axis of rotation. I can draw it in this way. This rotation. This is. I'll make it dash. The dash line is a trajectory of one point of rigid body. Trajectory of one chosen point of rigid body is drawn with dash line. In first moment, at initial moment of time, we have radius vector r1. At final moment, it is r2. Here r1. I have no enough place. R2. R1, R2. The angle of turn is delta phi, for example. Delta phi, it is here. I can delta phi. And we decided that angular velocity is without vector. I'll do this. Angular velocity is the first derivative from angle by dt. Angular velocity I'll write this. Angular velocity. This is angular velocity. And in the same way, we can describe angular acceleration. Angular acceleration. Angular acceleration. We can describe in the same way. Angular acceleration. We will sign it as beta, and this is a first derivative of angular velocity by time, d omega by dt, and it is equal second derivative second derivative from angle of rotation by dt. Angular acceleration. And the question is how to connect angular velocity and angular acceleration with velocity and acceleration, with velocity and acceleration that we talked about on our last lesson. Let's draw another picture to have a look at this. I'll draw it in this way. For example, if we have this is vector omega, angular velocity. This is radius vector of some point of rigid body. This is origin or reference point O. Here the radius of rotation R. This is angle P divided by 2. This is angle alpha, for example. You can see this is the same picture, but this is a projection to the screen. This is a projection. So what we can say about simple linear velocity? If we have rotation, the direction of rotation is shown by this arrow, and we can decide that that vector of velocity has direction that is shown here. So the vector of velocity is perpendicular to the screen, and the direction is from us to the screen, and v vector of velocity is perpendicular to the screen. And so how can we connect velocity and angular velocity? We can do it in this way. We can do it by this formula. It will be vector product omega r, and it is equal to omega r. And can you remember how to calculate the modulus of vector product? How to calculate the modulus of vector product? Maybe you can remember this. We can do it in this way. V modulus of vector of velocity. V is equal to omega r sinus alpha, and it is equal to omega r. It is equal to omega r. Do you have any questions about this? Do you have any questions? Don't have.
No.
Okay. Okay, that's great. If everything is clear, it's great. It's great, then we can continue. We can continue to start our studying process. In the same way, we can connect. We can connect. Acceleration and angular acceleration. For example, tangential acceleration. Tangential acceleration is equal. Tangential acceleration is equal to vector product omega omega beta. Omega multiplied by beta. Omega. It was the first lesson today, and I still feel asleep after this. Beta r, of course, in this way. Of course, in this way, and it is equal. And it is equal to beta vector r. And in scalar form, it will be like this. Will be beta r sin alpha, and it is equal to beta r. And if we have also we always have normal acceleration when we consider rotational motion, and normal acceleration is equal to omega multiplied by v, and it is equal to double vector product. It will be double vector product, and we can also write this in scalar form. In scalar form, it will be an is equal to v in second exponent, divided by r, and it is equal to omega in second exponent multiplied by r. And we can also calculate full acceleration. It will be square root from tangential, square root from squares of tangential and normal accelerations. Sorry, it will be in second exponent, and it is equal to r square root beta in second exponent and omega in fourth exponent. Okay, do you have any questions about kinematics of rotational motion?
Teacher, what is this? This is the tangential acceleration, and this is the normal acceleration. What is this? It's just the acceleration of the
Tangential acceleration means change of velocity by module, change of absolute value of velocity. This is tangential acceleration. Normal acceleration is change of velocity by direction. And full acceleration, full acceleration is vector sum of tangential and normal accelerations. This is full acceleration. The angle between tangential and normal acceleration is equal to 90 degrees. 90 degrees, or p divided by 2 radians. If we draw this, for example, tangential acceleration, normal acceleration, and we can draw sum of these vectors. It will be full acceleration. Let's draw this. Yes, it is here. This is full acceleration. Sum of tangential and normal accelerations. And according to this, we will get this formula. Do you have any more questions?
Teacher, here is 4. 4.
It is number 4.
Okay, thank you. No question, teacher.
Okay. It is number 4 because we made it like this. second exponent of second exponent, and it results fourth exponent. Okay, any more questions?
No, teacher.
No. Okay. Okay. Let's have a few words about planar motion. What is planar motion? Planar motion of rigid body is motion when all points of body move in parallel planes. This is plane motion, and plane motion plane motion can be considered like a sum or like a combination of linear motion and rotational. Combination of rotational and linear motion. It will be planar motion. And now we have finished to search or to learn kinematics, and let's start to speak about dynamics. Let's speak about dynamics. In kinematics, we learned motion without taking into account factors that may affect on this motion. And now we will take into account these factors. These factors are known as forces. Force is a physical value. That can be measured in newtons. It's named by name of famous British scientist Isaac Newton, who discovered three fundamental laws of dynamics. There are three laws. The first, Newton's law, can be described like this. Newton's first law of motion. Maybe I can print this. I can print this here. Newton's first law of motion. First law of motion. Newton's first law of motion. It can be written like this. Every body continues in its state of rest or of uniform motion in a straight line. In a straight line unless it is it is compelled to change it is compelled to change that state by forces sorry, it will be here forces by forces by forces impressed upon it impressed upon it Newton's first law of motion. What's wrong with this? Oh. Yes, okay. Okay, here you can see on the screen Newton's first law of motions. Reference systems where we have Newton's first law of motions are known as inertial reference systems. There is this law. This law is true. This law is true in inertial reference systems. What are inertial reference systems? They are systems that move with zero velocity or with constant velocity, with constant velocity along with direction inertial systems may or can move only along a straight line. Can move only along a straight line with constant velocity. So if we have acceleration, if reference system moves with acceleration, it is not inertial reference system. So inertial reference system can move only without acceleration and only along a straight line. I hope is it clear. So and what we have in the situation when there are some forces impressed upon body. In this situation, we have Newton's second law of motion. Newton's second law of motion can be written in this way. Newton's second law of motion. Newton's, like, let's make it red. Newton's second law of motion. Newton's second law of motion can be written in this way. What's wrong with this? first derivative dp by dt, it is equal to d by dt from product mv, and it is equal to force impressed on body, or impressed on body with mass equal to m. Okay, and what is p? P is momentum. Physical value that is known as momentum. Momentum, and it is equal to mv. M, you know that it is physical value known as mass. It can be measured in kilograms or kilos. V is velocity, and P is momentum. And there is a very important partial case when mass is constant. I'll write this when m is equal to const. When m is equal to const, we can write Newton's second law in this way. Ma is equal to m first derivative of velocity by time. It is also equal to second derivative from radius vector by time, and it is equal to force impressed on mass m. Impressed on mass m. Impressed on mass m. Do you have any questions about this? No questions. Okay. If we have not one force, but we have a few forces, we should use this vector sum, like this. We should use this if we have a few forces. So we can calculate this sum. We can calculate this and substitute it to our formula. I hope that it is clear, and if you have some questions, you can ask them. If you don't have questions, let's have a look at some common forces forces that we can have during our exercises. Okay, let's have a look at some forces. Okay, I will clear my board. The first type of force is elastic force. What is this? Let's draw a picture. Imagine that we have a wall. We have a wall connected to the spring. And the spring connected to the rigid body. And imagine that we move, or that we changed a place of this rigid body, and we changed the length of the spring, changed by the value of x. So we extended our spring by value x. So x is extension. In this case, when extension is small, we have Hooke's law. Hooke's law. What does it mean? It means that force known as elastic force. This is the force that tries to prevent spring extension. This force tries to prevent spring extension. Is equal to minus k x. X is extension. I will write absolute value without vector. Where key is a spring constant. This is a coefficient. It is a characteristic of spring, and it is known as spring constant. Spring constant. So it is signed as key. X is extension. Extension of the spring. Do you have any questions about this? No questions. There is another form of Hooke's law. Imagine that we have a rod. Like this. Rod, I mean cylindric body, cylinder with long cylinder, like this. The square of its cross section is equal to S. And the length of it is equal to L. And let's consider some extension of this rod. Some extension. Make extension is equal to delta L. We can write Hooke's law in this case. We can write Hooke's law. In this case, I will consider modulus. So I have no minus in this case. So we can write this like this. K delta L. And we can write this in this way. K L modulus delta L divided by length L. And we can also divide right and left side of this formula by square of the cross section S. So we can write this way: F divided by square of cross section equal to K L divided by S delta L divided by L. And we have got another form of Hooke's law. Another form. There are some signations. It is equal to sigma. This is equal to, and this is equal to epsilon. So we can write Hooke's law in this form. This is also Hooke's law. But in another form. Sigma is equal to multiplied by modulus of epsilon. Where is constant known as Young's modulus. This is a constant, but this constant depends on material. Of the rod. This constant depends on material. And what is sigma? Sigma is tensile stress, physical value known as tensile stress, and epsilon is also known as relative elongation or relative extension. It is epsilon. So we can also write this. Sigma is equal to F divided by S, and epsilon, I will I will clear my screen. I will clear my screen. So it is tensile stress, tensile stress, and relative elongation, or relative extension, relative extension. Relative extension epsilon is equal to delta L divided by L. Do you have any questions about the elastic force? Do you have any questions about this? Don't have. Okay. Okay. Let's have a look at gravity force. What is gravity force? Gravity force is the force that acts between two mass. For example, M1, M2, two mass. The distance between them is equal to r, for example. The distance is equal to r, and according to Newton's law of universal gravitation, I will print this. Newton's law of universal gravitation. Universal gravitation. Newton's law of universal gravitation. According to this law, force of gravity is equal to G M1 M2 M2 divided by R in second exponent, where G is gravity constant, and it is equal 6.673 multiplied by 10 in minus 11th exponent. Newton's square meters divided by square kilograms. Newton's law of universal gravitation. Do you have any questions about this? Do you have any questions?
No.
No. Okay. Okay. Let's have a look about gravitation force. Gravitation force near the surface of our planet. If we use Google, for example, we can find that mass of our planet, mass of Earth is equal to approximately 5.97 multiplied by 10 in 24th exponent, kilograms. And our planet has radius that is approximately equal where it is 6.37 multiplied by 10 in 6 exponent meters. And if we use Newton's law of universal gravitation, we'll have this. For example, mass multiplied by acceleration, it is equal to force. Now we consider a body that falls freely. So only gravity force is impressed upon it. Only gravity force. So this body falls for free. So only gravity force acts on it. And we have according to the Newton's law of universal gravitation, G M E divided by R E in second exponent. And we can write this in another way. M multiplied by G M E divided by R E and we can make a summation is equal to G. So we have mg, where G is acceleration of free falling body. Acceleration of free falling. It is equal to G ME divided by R. Oh, second exponent or second order. Second exponent, and it is equal to 9 0.81 meters divided by seconds. I will write in this way: seconds in second exponent. Acceleration of free falling. Acceleration of free falling. This acceleration is the same for all bodies near the surface of our planet. Well, it can be different. It can be different for different geographical regions, but approximately it is equal to this value approximately. For example, on equator or in other place, it will be some different, but not serious, not significantly different. Do you have any questions about this?
No.
Okay, so near the surface of our planet, gravity force can be calculated by this formula. F is equal to m multiplied by g. Okay, and the last force to learn for today is force of friction. Let's have a look at the picture. Like this. We have a rigid body that placed on horizontal plane, and let's study forces. Let's study forces that impressed on it. First of all, we have gravity force. Gravity force is equal to mg. This is a gravity force. And we also have force of normal reaction. Why do we have this force? We have this because there is no motion. Up or down. Then it means that we have force of normal reaction, and we can write that m plus mg is equal to 0. Because we have no motion up or down, and absolute values of these forces are equal. N is equal to mg by modulus. And let's set this body in motion. And, and, uh, 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 and, with velocity is equal to v. If the surface of the plane is rough, there will be a friction. There will be friction between surface and our body, and we have to take into account a friction force. Friction force can be drawn like this. F friction force, or force of friction, and according to friction law, friction law, or law of friction law of friction, friction force of friction can be calculated mu multiplied by n, where mu is constant. It depends on surface of body and the surface of plane. This is coefficient of friction. Coefficient of friction. How to print this? Coefficient of friction. Coefficient of friction. Coefficient of friction. Coefficient of friction. What questions do you have? No questions. Okay. There were forces. Some forces that we have learned. It was these was forces. Elastic force, gravity force, and a force of friction. We will use them on our practical exercises. And now we will consider two material points with masses m1 and n2, and I'll draw them. Material point with mass m1, material point with mass m2, and there is interaction between them. There is some interaction with forces F1, 2 and force F2, 1. Force 2, 1. I'll clear this. So we have two material points and interaction between them with forces F12 and F21. These forces are also called internal forces. For material systems that consists of these points, for these material systems, forces 1, 2, and 2, 1 are internal forces. So in this system, there is no external, not any external force is here. Not any external force, only forces internal forces between parts of material systems. They are internal forces, and in this case we have, according to the second Newton's law of motion, the momentum of material system is equal to momentum of first point plus momentum of the second point. Not momentum, derivative from momentum, and it is equal to 0. Why 0? 0 because we don't have any external forces. Because of this, we have 0 in the right side of our formula. But these derivatives, dp1 by dt and dp2 by dt, they are equal according to the second Newton's law. They are equal to internal forces F1, 2, and this F2, 1. So we can make a conclusion that F1, 2 plus F2, 1 is equal to 0. And we have got formula F1, 2 is equal to minus F2, 1. Minus F2, 1. And what have we got? We have got the third Newton's law of motion. I can print this law because it will be more useful to print this, more useful and more convenient for us. The third Newton's law of motion. Newton's law of motion. And what can we say about this law? According to this law, to every action to every action, there is always opposed and equal action, or equal reaction, sorry. Equal reaction, or the mutual actions of two bodies, upon each other, are always equal, and directed to contrary paths, and directed to contrary parts, and according to formula, it can be written like this. It can be written in this way according to formula. Oh, I'll make red frame because this is also fundamental law of physics, the third Newton's law of motion. Do you have any questions about this? No questions. Okay, I'll clear my screen. I'll clear my screen to make some free space on this, and we'll continue. Let's have a look at material system, any material system with many external and internal forces. According to the second Newton's law of motion, we have formula. The first derivative of momentum by time is equal to the sum of forces. And we have to write sum of internal forces, I, K, and I will write upper index I. It means internal forces, and plus sum of external forces, and upper index E means external. But what do we have? According to the third Newton's law of motion? We can reassign these indices, I, like IK, Ki. And according to according to the third law, Newton's law of motion, we will get that sum of internal forces for any material system is equal to 0. So momentum of material system can only be changed by external forces, and not by internal, by external forces only. Momentum can be changed only by external forces. And what will be if we have sum of external forces equal to 0? We will have this situation. So if sum of external forces is equal to 0, we can make a conclusion that first derivative is equal to 0, and if derivative is equal to 0, it means that function is constant. So momentum is constant when sum of external forces is equal to 0. Sum I sum of momentums of material points, it is equal to mi v I, and it is equal to constant. And it is equal to constant. And what we have got? We have got the law of conservation of momentum. Law of conservation of momentum. Law of conservation of momentum. According to this law, if sum of external forces is equal to 0, momentum will be constant. Do you have any questions about this? No questions. Okay. And the last what we will learn for today is center of mass. What is this? What is what center of mass is. I will clear some space on my screen. Center of mass. Center of mass is a point with radius vector defined by formula. Center of mass. Center of mass. Center of mass. It has radius vector is equal to m1 r1 plus m2 r2 plus mn rn divided by m. This is for discrete systems of n material points. M is the mass of whole material system. So it is m1 plus m2 plus mn. Or if we have rigid body, you can I can print this center of mass of any material system. For any material system, and a center of mass. I'll make a frame, and the center of mass. Center of mass of rigid body. Center of mass of rigid body. RC. RC is equal to triple integral R rho as a function of R dV divided by m. M is mass of rigid body. Mass of rigid body. Rho is density of rigid body. As you can see, to find the radius vector of center mass, we have to calculate integral, but it is not always necessary. Because there are some useful properties of center of mass. For example, if material system has a plane of symmetry, the center of mass will be on this plane of symmetry. If material system has the axis of symmetry, the center of mass will be on this axis. And if a material system has center of symmetry, the center of mass will be in this center. For example, if we have homogeneous cylinder, like this cylinder, the center of mass will be on its axis of symmetry. I'm draw this axis with dash line. And so the center of mass of homogeneous cylinder will be here. Here, this is center of mass. I can sign it by C. And for the last, why the center of mass? Why the center of mass is useful? Why it is useful? Why it is useful? Let's take first derivative from this formula. M d RC divided by T is equal to M1 d R1 dt is equal to, not equal, sorry, plus M2 GR2 divided by dt plus mn drn by dt. And what do we have? This is velocity of center of mass. This is velocity of point M1, and this is velocity of point V2, and this is velocity of point Vn. So we have here we have M V C is equal to M1 V1 plus M2 V2 and plus MN VN. But product of mass of mass and velocity is momentum. So we have sum of momentums P1 plus P2 plus Pn. So we have momentum of whole material system P. And let's take another derivative from this formula, from left and right sides of this formula. M d velocity dvc by dt is equal to dp by dt, and according to the formula in red frame, we have that it is equal to the sum of external forces. The sum of external forces. And what do we have? We have a formula that known as a theorem of center of mass motion. Theorem of center of mass motion. It allows us to consider material systems motion like motion of one material point. Placed in the center of mass. Okay, do you have any questions about this? Okay, if you have no questions, oh, yes.
What is that?
It is lower index C.
Okay.
Any more questions? Lower index C, the first letter of center, because we have learned center of mass. Okay, if you don't have any more questions, we can finish our lesson. I hope that we will meet again tomorrow. And have some exercises. And we will learn how to use this theory and formulas that we have learned before. Okay.
Okay, teacher.
Okay, teacher.